Hello, let's learn about carbapenem-resistant. Let us first understand what is drug resistance. Bacterial resistance to antibiotics has become a major public health issue worldwide. Microbes have the inherent ability to change their genetic material to favor their growth. Antimicrobials are used to either kill or suppress those microbes and to have they change their genetic material so that they can escape the effect of such drugs, leading to a phenomenon called antimicrobial or drug resistance. So from the you can see from the slide from the year the antibiotics are discovered. Say from 1941 the penicillin was discovered. By the year 1942 the penicillin resistance was reported. Vancomycin was introduced in 1956 while methicillin was introduced in 1960, and by the year 1961 methicillin resistance was reported. Linezolid was introduced in 2000. However, linezolid resistance was reported far before it was discovered, that is 1961. Daptomycin introduced in 2003, while its resistance was reported in 2005. So, to conclude, that within years of discovery of the antibiotics and by 1 or 2 years, the resistance gets reported. Hence, Sir Alexander Fleming rightly said that the microbes are educated to resist penicillin, and a host of penicillin-fast organisms is bred out. In such cases, the thoughtless person playing with penicillin is morally responsible for the death of the man who finally succumbs to infection with the penicillin-resistant organism. I hope this evil can be averted. So, what is carbapenem resistance? Rising resistance is of particular concern for gram-negative bacilli such as Pseudomonas aeruginosa, Acinetobacter, and Enteropacter. The latter being the most important pathogen for mankind. Carbapenems are the last resort antibiotics for treating infection due to gram-negative bacilli. Resistance due to carbapenems in this species is related to either due to combined mechanism of resistance, that is overexpression of broad spectrum beta-lactamases together with FS pumps, impermeability, or expression of the carbapenem heterogeneous beta-lactamases known as carbapenemases. So mechanism of resistance may be either to carbapenem related or non-carbapenem related. Carbapenem related is due to the true expression of carbapenemases. Carbapenem related mechanisms of carbapenem resistance, on the other hand, are mostly plasmid encoded, making them highly transferable, at least within the enterobacterial species, and therefore potentially responsible for outbreaks. They are also largely associated with multi or pan drug resistance. While non-carbapenem related mechanisms of carbapenem resistance are not transferable. In addition, if the resistance mechanism involves purine deficiency, this could significantly impact bacterial fitness, contributing to a decreased rate of transmission. Isolates with carbapenems poses a great threat than those enterobacterial species that do not possess carbapenem activity. So, carbapenem resistance may be due to impermeability to carbapenems and by production of carbapenems. If because of impermeability, the carbapenem is not transferable and there is a low risk of transmission. However, because of the production of carbapenems, there is a high risk of transmission because it gets transferred to plasmid. Currently, the spread of carbapenem-producer is the most important clinical issue in antibiotic resistance. Gram-negative, particularly in carbapenems, belong to one of the three groups of beta-lactamases, namely ambler class A, B, and D. Differences between these carbapenem enzymes are clinically significant, and since their hydrolysis profile differs, their species distribution, their worldwide epidemiology is also different. Ambler class A penicillinases includes clavulanic acid inhibited penicillinases. The most widespread represented is KPC, that is Klebsiella pneumonia carbapenemase. Then ambler class beta lactamases include metallo-beta lactamases. Ambler class D beta lactamases include oxacillinases. So this is a table where you can get it's like a guide wherein you can see there are antibiotic classes in one column, the main antibiotic representatives in another column, and based on the detection of the enzymes, the particular antibiotics could be selected. Like we have the penicillinase, cephalosporins, acquired low level penicillins, then inhibitor R penicillinase, acquired high level penicillinase, ESBL, AMC, carbapenem-resistant, carbapenem-resistant Pseudomonas, carbapenem ambler class A penicillin, and other such. So the red ones are the resistance, while the yellow ones are the decreased susceptibility, while the greener ones are the susceptibility. What is the extent of the spread of carbapenem-resistant bacteria? The spread of carbapenem resistance is by impermeability or by the production of carbapenem-resistant enterobacter isolates that do not produce a carbapenems are mostly Klebsiella pneumoniae and Enterobacter that usually express decreased permeability associated with CTX or CTX-M type enzyme or overexpression of cephalosporins, respectively. Although epidemiological data for this carbapenem-resistant isolates is limited, the prevalence rates appears to be vary significantly. So, Klebsiella pneumoniae is mostly because of impermeability and expression of CTX-M enzyme. While Enterobacter species also is because of impermeability and expression of AMP enzyme. The spread of carbapenemase producers like class A penicillinase, example is KPC enzyme. They are currently the most clinical significant enzymes among the class A carbapenemase, and the first KPC producer was identified in 1996 from Eastern USA. And they now have spread worldwide, and even though the KPC enzyme still most identified in pneumonia. While about class B, the MBLs are known to be intrinsic in many environmental species. However, since the early 1990s, they have been identified as acquired enzymes in Pseudomonas and Enterobacter. The most common MBLs include VIM and IMP groups together with the emerging NDM group, whereas others such as GIM, SMP are mainly sporadic. Although reported worldwide, the VIM producers in Enterobacter are highly prevalent in Southern Europe and Mediterranean region. One of the most clinically significant carbapenemase is NDM, that is New Delhi metabeta-lactamase. It was identified coincidentally in 2019 in Klebsiella pneumoniae and E. coli isolate from patient in Sweden hospitalized in India. The main identified reservoir of NDM was in the Indian subcontinent, Pakistan, India, and Sri Lanka. These countries are experiencing multiple ongoing outbreaks of different NDM producers. The prevalence of carriage in this region is estimated to be about 5 to 15%. So Enterobacter, Klebsiella pneumoniae and E. coli, the metallo-beta include VIM, IMP, and NDM. Pseudomonas aeruginosa, Acinetobacter, VIM, IMP, and NDM. The first identified oxa producer, which belongs to the class D oxacillinases, was a Klebsiella pneumoniae isolate record from Turkey in 2003. Therein, there has been reported many outbreaks from the North African countries and from Middle East and India. Oxa 163 differs from Oxa 48 by single amino acid substitution. Its carbapenemase activity is almost undetectable, but profiles include broad spectrum cephalosporins and its activity is partially inhibited by thiaminic acids. Oxacillinases with carbapenemase activity in Enterobacter, Klebsiella pneumoniae suggest is mainly because of Oxa 48, but in Acinetobacter pneumoniae it is Oxa 23. Now let's see learn about what are the clinical aspects of the infection of carbapenem-resistant gram-negatives. They include UTI, peritonitis, septicemia, pulmonary infection, soft tissue infection, and device-associated infection. The vast majority are UTI, and no specific clinical manifestation have been reported. The sources of community-acquired infection because of KPC, IMP, VM are hospital-acquired infections. Oxo-14 and NDM are hospital and community-acquired infections. UTI infections, peritonitis, septicemia, respiratory tract are the main types of infections because of carbapenem-producing enzymes. Carbapenem-resistant gram-negative are also multi-resistant to non-beta-lactam antibiotics, with the exception of imipenem-resistant Pseudomonas aeruginosa, which may remain susceptible to several broad-spectrum antibiotics. The choice of the optimal antibiotic therapy is largely dependent on the detailed analysis of the antimicrobial susceptibility pattern. Antibiotics should not be used monotherapy in order to prevent further selection of antibiotic resistance and theoretically improve clinical efficacy. Carbapenems, if they are exhibit low MIC values, they should be administered for treating carbapenems produced at a higher dosage and prolonged infusion regimen, and preferably in association with an aminoglycoside or a cholesterol. 20% of the oxo-14 producers do not produce an ESB and may remain susceptible to extended spectrum cephalosporin. Treatment alternatives due to imipenem-resistant Pseudomonas aeruginosa with OPRD2 modification. They include broad spectrum cephalosporins, aminoglycoside, and fluoroquinolones antibiotics, to which many strains remain susceptible. The combination of antibiotics should be preferred to monotherapy. Again, meropenem, colistin, and fosfomycin or parenteral rifampicin may be included in the antibiotic combination. Treating infections due to carbapenem-resistant Acinetobacter, TG and colistin have been proposed, but optimal treatment remains unknown. For Enterobacter, colistin, fosfomycin, gentamicin, tigecycline in bi or tri therapy, or carbapenem at a high dosage plus prolonged infusion and plus aminoglycoside or colistin. The Pseudomonas aeruginosa impermeability. If impermeability is the cause, then broad spectrum cephalosporins, aminoglycoside, or fluoroquinolones. Or if carbapenemase enzymes produced, then meropenem, colistin, fosfomycin, or rifampicin. For Acinetobacter, how many colistin and tigecycline? It will be the treatment of choice. So that was all about carbapenemase. Thank you.